When we look up at the night sky, space looks calm. It looks empty. It looks like a quiet, uniformly cold void between distant stars, where nothing much ever changes. This is the image we carry in our heads, a gentle, dark canvas, dotted with steady points of light that have shone the same way for thousands of years. We grow up thinking this is the natural state of the cosmos, empty, quiet, unchanging. But that image is wrong, deeply wrong. The universe is not a calm place. It is full of locations so violent, so extreme, that no object can survive within them for more than a few minutes. These places do not just break physical laws we think are fixed. They rewrite what we think is possible. The scariest of these places are not the distant black holes we see in science fiction movies. They are stars. Stars that burn so bright, pull so hard, and tear themselves apart so quickly that they make every danger we know on Earth look like a gentle breeze. We do not see this violence from our spot on Earth. The light that reaches our eyes is smoothed out, softened, stripped of its raw power. The single most unforgiving example of this stellar violence sits 15,000 light-years from our planet. It lives inside one of the most famous star-forming regions in the southern sky, the Carina Nebula, a cloud of gas and dust where thousands of new stars are being born right now. This particular star did not form gently, and it will not die gently. Its name is HD 130458A. It is a young hypergiant. It is not the biggest star astronomers have ever catalogued. It is not the heaviest star we have ever measured. It holds no cosmic records for raw size or total mass, but it holds one unenviable title. It is one of the most actively self-destructive stars we have ever observed. It is not waiting millions of years to reach the end of its life and explode. It is tearing itself apart right now, as we speak. It comes apart from the inside out, one particle at a time, shedding its own mass faster than any physics we once thought possible. Every passing month, every passing year, it pushes more of itself out into the surrounding nebula, carving away at the gas around it and rewriting the shape of the entire region. It is a preview of just how brutal the universe can be when the rules that keep our own star stable get thrown out completely. To understand why this star is destroying itself, we start with a rule that applies to every star in the universe. The bigger a star is, the shorter its life will be. A small red dwarf can burn steadily for trillions of years. Our own sun will live a comfortable 10 billion years before it runs out of fuel. HD 130458A will be lucky to survive 3 million years total. Right now, it is already losing 500 times more mass every single year than the sun loses in the same span. That adds up to 1 full moon's worth of mass pushed out into space every single month. The same force that keeps our sun warm and stable is the ticking time bomb inside this star: nuclear fusion. HD 130458A is 120 times more massive than the sun and 4 million times brighter. Its core cranks out energy so fast that the outward pressure from radiation is stronger than gravity's inward pull. Gravity can barely hold the star together at all. Every layer of its atmosphere gets pushed away into space, creating a violent, roiling stellar wind that moves at 7 million kilometers an hour. That wind does not just drift gently into the void. It slams into the surrounding gas of the Carina Nebula with incredible force. It carves huge cavities into the cloud and heats the interstellar medium to 10 million degrees Celsius. This is not slow, gentle erosion. This is a constant, relentless bombardment that reshapes the entire nebula from the inside out every single day. This level of constant violence is already extreme enough to break most cosmic rules. But the first twist in HD 130458A's story is far more surprising. You would assume a star tearing itself apart would just blow apart completely in a few 100,000 years, and that would be the end of it. That is not what is happening here. The star is so massive that gravity still clings to it in fits and starts. It cycles between swelling outward when fusion output spikes and shrinking back when gravity temporarily pulls harder. Every few thousand years, this back and forth erupts into a giant, catastrophic spasm of mass loss. The star does not just shed particle by particle. It throws off an entire shell of material equal to the entire mass of our sun, and it does it in just a few short decades. These new, fast-moving shells do not drift out into empty space. They slam straight into the older, slower layers of gas the star ejected thousands of years before. The collision creates enormous, roiling shock fronts that compress and heat the gas until it glows brighter than most entire galaxies. This is not a steady burn. It is a cosmic fireworks show that lights up the entire Carina Nebula for thousands of years after every ejection. The repeated waves of violent mass loss have carved a huge, dark cavity into the heart of the nebula, shaped like an old iron keyhole. We call this feature the Keyhole Nebula today. It is not a natural formation. It is a permanent scar carved directly by HD 130458A's relentless self-destruction. Every violent spasm, every layer of ejected gas, every shock wave that lights up the nebula starts deep inside the star, where the chaos grows more extreme by the second. We have looked at the damage this star causes outside its own boundaries. Now step across its surface, down into the core, and see what drives this whole process. Fusion does not stop at hydrogen here, the way it does in our sun for billions of years. It accelerates, jumping from one element to the next, faster and faster as the star runs out of lighter fuel. First, it burned all its hydrogen into helium, just like any star. That step took just a few 100,000 years, not the billions our sun will take. Then it fused that helium into carbon, a step that took even less time. Right now, it is burning that carbon into heavier elements, at a breakneck pace that would shock anyone used to the slow, steady burn of a normal star. Every time fusion moves to a heavier element, it releases less energy per unit of mass. To keep the fusion reaction going, the core has no choice but to contract. Contraction cranks up the temperature and pressure even higher, which pushes the reaction to jump to the next heavier element even faster. This creates a feedback loop that never slows down. It only accelerates. Every extra blast of heat from the contracting core pushes the star's outer layers even further outward. Gravity's already weak hold on those layers stretches thinner and thinner. More material slips free. More mass blasts out into space, and the feedback loop spins even faster. The star is eating itself from the inside out, one element at a time, and there is nothing to stop the process. The core chaos that tears the star apart from the inside is terrifying enough on paper. But to grasp how deadly this star really is, we need to bring something familiar into its neighborhood and see what happens. Let's run a thought experiment. Imagine we launch a robotic probe toward HD 130458A and park it at 1 astronomical unit away from the star. 1 astronomical unit is exactly the distance between Earth and our own Sunday. At that distance from our star, a probe would sit at a comfortable 15 degrees Celsius. It could collect data for years without damage. It would work just like it does in orbit around Earth. The same distance around HD 130458A. The probe would be hit with 10,000 times more radiation than it would get at the same position around our Sunday. The temperature would start climbing instantly. Every sensor would fry within the first 30 seconds. In less than 3 minutes, the probe's hull would reach 3,000 degrees Celsius. Solid rock would melt. Every alloy in the probe's structure would turn to liquid. The relentless stellar wind, moving at 7 million kilometers an hour, would hit the molten probe, tearing it apart molecule by molecule. Within a few hours, not a single intact piece of the probe would remain. What was once a solid, functional machine would become nothing but a thin cloud of charged particles, blown away into the void by the star's endless wind. This is not a threat that requires you to touch the star. Even at a distance that is comfortable and life-giving for us, HD 130458A kills everything it touches, faster than most systems can even register the danger. HD 130458A does not just kill anything that strays too close while it lives. When it finally dies, it will take out a huge swath of its galactic neighborhood with it. Right now, even in its active self-destruction, it is already reshaping the Carina Nebula. Its relentless stellar wind compresses nearby gas clouds, triggering new waves of star formation that would never have started without its violence. But that is nothing compared to what comes next. When the star finally runs out of elements to fuse, when its core can no longer sustain the reaction that keeps it burning, it will not collapse quietly. It will not even explode as an ordinary supernova, the dramatic death most massive stars suffer. This star will detonate as a hypernova, one of the most powerful explosions the universe ever produces. The total energy it releases will be 100 times greater than a standard supernova. It will outshine the entire galaxy for weeks. A narrow, focused jet of gamma rays will shoot out from both of the star's poles, moving at almost the speed of light. That jet will carve a straight path through the galaxy, clearing all interstellar gas in its way for hundreds of light years. Any star with a rocky planet orbiting within 1,000 light years of the explosion, if the planet lies along the jet's path, will be scoured clean. The jet's radiation will strip the planet's atmosphere away in hours. It will cook the entire surface of the planet to temperatures high enough to boil away every drop of water. No complex molecule can survive. All life on the surface will be sterilized completely before any organism can even detect the blast. That level of destructive power is terrifying enough from a single star sitting 15,000 light years away. But the third twist in this story changes how we see the entire galaxy. For decades, astronomers assumed that stars this massive, this violently unstable, were extremely rare. We thought HD 130458A was a 1 in a million anomaly, a freak accident of stellar formation that barely ever happened anywhere in the universe. We thought that the chance of one of these explosions threatening any inhabited world was effectively zero, a risk so low we did not need to think about it. That assumption was wrong. New deep-field surveys of the Milky Way have mapped the sky in infrared, cutting through the dust and gas that hid these massive stars from our telescopes for centuries. What we found has forced a complete rewrite of our models of stellar evolution. We now know that hundreds of these violent hypergiants exist in our galaxy alone. Thousands more have been confirmed in nearby galaxies, orbiting right alongside thousands of smaller, calmer stars like our own. Each one of these hypergiants is a ticking time bomb, scattered at random across the spiral arm of the Milky Way. Some are already in their final death throes, counting down the last 1,000 years of their fusion life. Some have already burned through their fuel and are just waiting for their cores to collapse. They remind us that the quiet, dark sky we see on a clear night hides a far more dangerous reality. For most of the history of our galaxy, space was packed full of these giant, unstable stars, blowing themselves apart and reshaping the structure of the galaxy around them. Their violence has carved out the cavities we see in nebulae, compressed gas clouds to trigger new star formation, and scattered heavy elements across thousands of light years. They have always been here. We just did not have the tools to see them. You might be wondering right now if one of these ticking bombs is close enough to threaten us. The good news is clear. The closest hypergiant to Earth sits more than 1,000 light years away. Even if it exploded tomorrow, the gamma-ray jet would have to point directly at our planet to cause any harm. The odds of that alignment are extremely low. We are safe for now. But that safety does not mean we can ignore what places like HD 130458A teach us. We live on a gentle, stable planet, orbiting a gentle, stable star. We have grown used to this calm. We take it for granted, as if this is the natural order of things, the way the universe is supposed to be. That is a lie. Stability is not the rule. It is a rare, lucky exception. Most of the universe is violent, extreme, and completely hostile to any form of life as we know it. The scariest places in the cosmos do not just scare us because they can kill us. They scare us because they reveal just how fragile our own peaceful existence really is. And here is the core paradox that sits at the heart of everything.